So looking at the posts from Jarl, Fantasy Colony Simulator on 2D grass rendering with web GPU compute shaders. So it's fully procedural grass renderer. It's 2 compute passes to generate, depth sort, and shade all the visible animated pixel art grass for each frame. Game runs in a customized Bevy fork on WGPU. Live demo runs the same shaders in your browser. So it's 2D Viking Colony Simulator, pixel art, 2D global illumination, procedurally generated world that streams in chunks. A bunch of that world is open meadow and forest floor, and the grass is on screen almost all the time. So it's got to be procedural, cheap enough to cover most of the map, fit the pixel art look, react to lighting, wind, and creatures moving through it. So here's what the world looks like, and an example of the actual grass running in the browser, which is pretty cool. Actually reacts to your mess and stuff.
Yeah, on a fancy browser that supports no GPU. Sorry, I looked at this earlier and I couldn't get things to load, so don't fault you.
Yeah, it's on Firefox. I guess that's interesting. Usually it's the one that doesn't support things.
It's Linux that doesn't support it, no.
So we've got grass as an image, not geometry. So it's 2 compute passes to regrow every blade from a hash each frame, and 1 atomic max per pixel serves as a depth test. So the final result borrows a lot of techniques. Main inspiration comes from GPU gems rendering countless blades of waving grass, Ghost of Tsushima, John Wick's 2D grass, God of War's wind system. Yeah, so this one. Broader survey of how games render grass. There are a couple of overview videos. More general building blocks. United's World Pax World Depth Test, PCG hashing, and blue noise culling are introduced and credited in the sections where they appear. I'm not sure what they're using from Nanite. Pax World Depth Test. Or Pax Word. Oh, no, okay, right, that's the atomic. Okay, yeah, we'll get there, I guess. Demo above runs in the browser through web GPU. Modern Graphics API lives in the browser. Also native apps. Big advantage is more control over GPU and access to compute shaders, which is what this work leverages. Able to share a good amount of rendering code with Bevy. Demo is mostly an illustration, does not necessarily hit the same performance targets. Camera sits much closer than the games, which is expensive configuration for this algorithm. However, to bend the grass, left drag is pan on the demo. Side panels show the intermediate targets, is the blade depth, the raw atomic buffer, and the wind field. Yeah, okay. So, system unit with treats the grass as an image rather than geometry. So, to keep things simple, there's no blade entities, no meshes, no persistent state. Every frame, 2 compute shaders regenerate every visible blade from a hash and write it pixel by pixel into a buffer that the compositor then sorts into the scene. This is not the fastest possible approach, but is a reasonable one for our performance target. This stage runs in 4K, way under 1 millisecond. So every frame, the grass is rebuilt from scratch. Compute shader walks the visible screen tiles, asks for a small density texture, how much grass grows there, generates each blade from a hash of the tile coordinates and the index. Hash provides everything the blade is, Position on the tile, the height, the color variation, and the sway phase. Because the hash inputs are world coordinates, the same blade appears in the same place every frame, no matter where the camera is. So basically, get a tile position, load from a texture, get the density, some kind of blade count from the density, and PCG hash. Okay, yeah. One frame of the demo is data, numbered in pipeline order. So density read, wind field, atomic buffer, unpacked color, blade depth, and the final composite. The first is the density mask, how much each tile wants. Dark spots are bare ground. Wind field brightness is just the gust strength. A couple overlapping sine waves. The atomic buffer is the result of the first pass with one integer per pixel. Each integer packs 3 values. The blade depth, that's the root row on screen, how far up the blade the pixel sits, and a color variation seed. In the panel, red shows the depth and green is the position along the blade. So they're packing some data together and then they're visualizing it as 2 gradients on the image there. So blade depth is where the blade is rooted on the screen. So this is for sorting during compositing. Then the final compositing is with everything merged. Individual blade starts as a handful of numbers from the hash, root position, inside the tile, height, color seed, and sway phase. To draw it, the shader walks from the root to tip 1 pixel at a time and offsets each row sideways by the local wind and creature velocity bend. The tip moves farther than the root, so the column curves. Blade is 1 to 3 pixels wide and a few dozen tall, so drawing is only a few dozen writes to the buffer. So iterating through the rows, get the height gradient, get a displacement scaled by the height, so you get kind of a curve shape to it. Right, solve for a pixel X and Y, and then right to the buffer. So these are captures from the demo renderer with density turned down. So the tile grid with the hashed blades, then 1 blade magnified, first in column error, and then 1 with the wind turned on. The same blade in both close-ups from the same hash. Right. Where the blades overlap, a packed integer compared with the atomic max function decides which one owns the pixel. The comparison itself is the depth test. Second compute pass reads the winning values, colors them into an image with a root to tip gradient, and fills into aliasing pixels along the edges. Pulse trick fits in 2 lines by bit shifting to the most significant bits. That's going to be the predominant factor when you do the atomic max. So this is actually the kind of a sort criteria, and then everything below that is kind of a more or less like a payload kind of idea. This is cool. I've seen this a couple of places recently. Compositor places that image into the scene. Each grass pixel carries the blade's root position, and the compositor compares the pixel against the feet of sprite and walls. So a blade can pass in front of a character's boots and behind their head. Lighting and fog can apply to the rest of the scene and apply to the grass as well. Sections go through each of these stages in detail. along with some of the optimization work behind them. We've got the input data, is the density, wind, and the floor mask. So nothing exotic to feed the system. Everything in the 2 passes arrives in a handful of small textures. 5 inputs are density texture with 1 value per map tile, saying how much grass is there. It's aligned to the world grid, not the screen, so that the pattern stays fixed as the camera moves. Wind and velocity. These are vector fields from the climate simulation. This is for displacement. So it's a small 3D volume. Okay, yeah. They barely don't need a 3D volume. So yeah, diffusion, iterative diffusion there, so that it spreads out. Floor mask texture is an off-screen pass, rendering only floors and rugs into a mask, so that the grass passes suppress blades pixel perfectly where players build floors rather than per tile, so block grass that would otherwise be drawn with the density texture. Blue noise texture from Christoph Peters for medium frequency blue noise. It's also looked up by world position rather than screen position, so it sticks to the ground. Parameter block with some 30 tuning values. It's from the debug panel above. Grass image is rendered at half screen resolution and scaled up during compositing. Performance section comes back to why this is this one decision matters more than anything else. So you have the textures feeding the grass generate and compute pass, doing the rates of the atomic buffer. Okay, I guess explain it. First the 4 inputs. Grass generate, hashes, bends, and rasterizes with the atomic operation. Grass unpack does the compute pass to decode the winning words, shade them, fill in the gaps for the anti-aliasing, and culling blades standing on floors. So grass color and grass depth, 2 outputs for color and depth. Compositor lights and shades the grass. Then perimeter block, just how they pack everything. Some nice visualization if you've got to deal with padding stuff. Okay. So generating grass blades and a compute shader. So the generate pass dispatches one 64-thread work group per 16 by 16 screen tile. Each work group finds the world tiles overlapping its screen tile, reads the density, and splits the blade work across the threads with a stride of 64. So one work group is rendering its tile. Each color gets a different thread. Each color represents a different thread. It's interesting way to do it. Animation also shows most threads sitting idle, which looks more wasteful than it measured. The null shader test attributed most of this, almost all of this passes cost to its atomic rights. And idle lanes are masked off and issue none of them. So on the hardware that they profiled, the empty reads were not a meaningful cost. They're saying, okay. GPU fills the gaps with, other work groups. Okay. The balance that did matter is the original 1 thread per tile version, where a single thread rasterized every blade of its tile. Splitting that work is where the speed up came from there. So each blade comes from 1 hash call, using PCG 2D. So they get a jitter value from PCG hash of world position and the blade IDX. Yeah. I guess that's okay. Because I have a calling logic there. So 8 bits for X jitter, Y jitter, blade height, color variation, sway phase, and per blade and frequency variation. Same title, same blade index, same seed. Tilde is identical every frame. Only the wind input changes. Survival check uses blue noise rather than a hash because hash culling produces white noise, clumps, and voids, where the blue noise produces evenly spaced survivors. Same as hashed alpha testing and the spatiotemporal blue noise. So motion combines two parts. It's a dual harmonic wind sway. A single sine reads as a metronome. So they've got two directions. Velocity push with the exponential easing that approaches a bend limit asymptotically. So it leans far over but never lies flat and never snaps back. Okay. Yeah. So they've got some sway term based on sine. It's based on some maximum velocity. Yeah. It's procedural tree wind. Procedural bias sample. We have quite a few links here actually. In this one, it's pretty cool. So yeah, showing a dense field mid gust. Okay, so sorting the overlapping blades with the atomic max depth buffer. The blades overlap, so something must decide per pixel which blade is visible. Instead of a Z buffer or sorting, each pixel is a single U32 with depth in the high bits, and atomic max selects the winner. Yeah, and because depth is in the high bits, numerically largest is the frontmost blade. Top-down 2D scene, larger screen Y, slower on the screen, closer to the camera. So it's just your convention you have to establish. Okay, so depth in bits 31 to 16, that's the root position on the screen Y for Z testing, more or less Y testing, I guess. The height is the position along the blade from 0 to 255 at the from the root to the tip, and this is for color gradient. And then yeah, just some seed for variation per blade. 0 means there's no grass. Nothing will have written to it. And blade tips above 95% height are never written. So we're tall. And short blade overlap. Ties break towards the shorter one instead of a floating tip. Rasterizer is a row loop with one atomic written per pixel. So iterating through the rows. Get a height weight. Call based on that. Cubic bending term. Right, yeah, so it's the amount that it curves based on the displacement. Yeah, solve for the packed value, and then yeah, iterating over the columns that it covers. Do the right with the atomic max. Yeah, depth test is an atomic max on the packed integer with depth in the high bits. Same construction as in NAND software rasterizer with a 64-bit word, 30 bits of depth, 27 of cluster ID, and 7 of triangle index, with an interlocked max used for clusters with the triangle edges under 32 pixels, where Epic measured a 3 times average win over the fastest hardware path. Jarl's version is a 32-bit 2D variant with the depth direction inverted for screen Y. For web GPU-oriented walkthrough of the idea, there's another one here. For current research, when a compute rasterization wins and loses, is a CUDA-based rasterizer. Reports 2 to 5 times wins on dense geometry and order of magnitude losses on low poly scenes. So one detail worth knowing, writes with equal depth are not a last write or wins race. The atomic max compares the entire 32-bit word, so the actual depth, the comparison falls through to the lower fields, larger height byte first, then larger variation. So ties are handled by the lower bits. The WGSL spec guarantees that atomic read modifier writes on one object are mutually ordered, and max is associative and commutative. So the rest is deterministic regardless of thread scheduling. Bit layout is effectively a priority function, so the tipmost sample wins. So you just invert it if you wanted to have the roots win. So both outputs for one frame, some same framing as the shot from above. The checkerboard showing where the alpha is empty. Oh yeah, just the background, yeah. So unpacking, shading, and anti-aliasing. The unpack pass runs 1 thread per pixel. Reading in the packed word plus the 4 cardinal neighbors provides everything for shading and anti-aliasing. A series of mixes. You got a height gradient, you got a per blade jitter, warm shift towards the tips, and an edge dimming where the pixel has few grass neighbors. So there's a couple of terms that play into the final color calculation. Anti-aliasing works on empty pixels. Grassy neighbors can become a half bright edge pixel, gated by blue noise. So it got some more color variation. Yeah, I noticed that they were doing it before. It was the way the edges is not. Yeah, they're using blue noise to jitter the edges. Yeah, this is also why depth lives in its own image. Anti-aliasing needed the alpha channel. Needed the alpha channel for coverage, so the blade root position moved to a separate texture. The floor mask checks, samples the mask at the blade's base position, not the current pixel. So blades rooted on a stone floor are culled entirely, but a blade rooted on grass can lean its tip over the floor's edge. Cost is 1 texture load because the mask is produced by an ordinary camera. Not sure exactly what's here. So they have a hangover thing, like that, yeah. Compositing grass with the world. I've got a 3-way depth sort. This stage is what makes the grass feel like part of the world rather than a layer drawn on top. This is each blade has a slot between floors, walls, and creatures at the right depth. Compositor receives grass color, grass depth, sprite layers, sprite height buffer per pixel. How high above its feet is the sprite pixel? Channel baked into the sprite atlases. It's kind of like an offset because you have a certain camera position. From those two, it computes 2 feet lines, makes one comparison per occluder. So their object feet, per pixel sprite height, then wall feet. So it's comparing the base position. So there's information to make a decision on that. Standard top-down convention, higher white renders in front. Yeah, applied per pixel in the compositor. Handling 2 types of occluder at once. The wall case has one subtlety. Comparing against the pixel's own Y creates diagonal cutoffs within a wall tile. So world Y is reconstructed and snapped to the 16 pixel grid. Interesting. Got a handle for alpha blending. It's kind of strange. I've got 3 different insertion points. Where it gets drawn with respect to the sprites, I guess. Yeah, floor, fog and shadow, then grass that's behind everything, then they draw the walls over top of that, then the grass that is drawn over the top of the walls, then any objects, and then grass that go over the objects, and then finally the UI or outlines. So it's based on comparison with objects and walls. Interesting. So paint order is so lit floor layer, drawing the floor, fog and shadow. Blades that lost both types of comparisons get drawn then the walls get drawn. Then these are blades that are rooted below the wall tile edge. Then objects, grass that character wades through. So 2 details, the grass is pre-fogged. So they apply a fog term. It's not reapplied redundantly with the fog and shadow. Same height-based fog clipping as sprites. So it all comes together. Pretty cool. So here's the velocity part of that chain. So if you have a runner leaving a wake, it's getting splattered into the velocity grid and decaying behind it, and how that influences the grass displacement. Making it fast enough to ship. So the first working version was slow enough to dominate the frame time. Null shader tests attributed almost all of that cost to atomic max scatter rates. So if it was to write less, so capping the number of blades per tile, its density formula, we could ask for hundreds of blades per tile, and the overlap means that almost all that was redundant. Capping that was a large win and invisible in the final image. Do a cooperative dispatch. Originally one thread rasterized all the blades in the tile. Splitting a tile's blades across a 64 thread workgroup measured roughly 4 times faster at full density. rendering at half resolution because it's fairly low frequency content, doing half the width and half the height, so it's quarter of the pixel count, and blade height and thickness shrinks with them, so you have equivalently quarter the amount of writes. And then they're upscaling pixel art, so almost no visual loss. Stochastic culling skips a fraction of blades by blue noise threshold cuts and writes proportionally. Threshold cuts writes proportionally and is visually free where the blades overlap. There were two that were not wins. Two things they tried that were not wins. Both informative. Shared memory tiling. Staging the tile in the workgroup memory was a regression. The buffer caused to register spill to local memory. Thread utilization was the entire win in this workload. Didn't get anything from the memory locality. Doing a read before the atomic. The idea was do an atomic load, skip the atomic max when the write would lose. Measures again about half slower. It's contingent write there doing that. Likely explanation is that the caches operate on 32-byte sectors, so the read generates its own memory traffic. Since the blades are thin, most pixels are written once and the check states nothing. Atomic throughput varies across vendors, so it should be remeasured on other platforms. Keeping bent grass connected under strong winds. So yeah, they're doing that row by row walk. Under a hard gust, you could fragment like this. Some comparison in motion. It does look a little bit nicer, but it's nothing huge. Yeah, just a little bit of fragmentation in them, the way that they draw the blades. The walk writes one pixel per row, so two consecutive rows stay connected only when the sideways step between them is at most 1 pixel. The bend curve concentrates movement at the tip. So, under a strong gust, the tip moves several pixels sideways per row. The blade splits into dashes. So, this is slope greater than 1. It's handled by Breslin's algorithm. So, the curve cannot be rasterized by stepping one axis when it locally runs faster along the other. The game's own camera keeps the step sub-pixel, so it took the demo's close-up camera and stronger bend to actually make it do that. Yeah, so that they don't actually have this artifact in practice. Improvement keeps the row sampling in bridges. Each consecutive pair of rows so when the blade is upright, n equals 1 and nothing changes. Under hard bend, the loop adds only the missing pixels. Height value interpolates along the blade parameter, so the root to tip gradient in the second pass stays correct. Underlying principle, stepping curve is roughly one sample. So one sample lands per pixel goes back to adaptive forward differencing and Wu's algorithm. Line drawing. One side effect is bridging renders whatever the math produces, including hooks. push a blade down hard enough and the curve folds back on itself. Okay, right now. Instead of dashes, you get a continuous curl. Looks like crushed grass. Okay. Yeah, so that's the whole system. Density, texture, wind field, 2 compute passes, an atomic max depth test, no persistent state, regenerated from hashes every frame. Stay consistent with the pixel art, sort correctly against sprites and walls, and are cheap enough to cover most of the world. For more conventional approaches, there's another post with comparison, another one about grass, using a geometry shader. There's another, in the Bevy ecosystem, there's a procedural grass implementation. There's another one handling environment scattering. For the compute side, some tutorials for WebGPU and WGSL specification. GDC talks on procedural grass and wind simulation in Ghost of Tsushima. It's a different scale.